Hi, I'm Takuro Fukunaga. In this video, I'd like to talk about my recent result on the coflow scheduling. Here is the summary of my paper. The main result of my paper is to show that the time index LP relaxation for the coflow scheduling has integrated gap at most 4. In this video, firstly, I introduced the coflow scheduling problem. Then, I formulate the time index LP relaxation for the problem. Finally, I give a proof for the fact that the time index LP relaxation has an integrity gap at most 4. The proof basically presents a rounding algorithm for LP solutions, but it doesn't run in polynomial time. Now, I introduce the coflow scheduling problem. The coflow scheduling problem is motivated by MapReduce. That is a popular framework used in the cluster computing. MapReduce forms a cluster that consists of two types of computers called mapper and reducers. During its computing, it incurs a lot of data transfer from mapper to reducers. To some study, Facebook data centers spend 33% of runtime for data transfer. Therefore, it is important to make this transfer efficient, and this process is formulated as this coflow scheduling. Mathematically, a coflow is defined as a bipartite multigraph. Let A and B be the given bipartition of the node set, and a coflow is a bipartite multigraph defined with this bipartition. Here, each edge joining nodes A and B represents the demand of transferring a unit of data from A and B. We are given several coflows defined on the same node set, and consider scheduling data transfer to satisfy all demands of coflows. We consider discrete time schedules. That is, the time horizon is divided into discrete rounds, and the schedule specifies which demands are processed in each round. We also have a constraint that each node communicates with at most one other node in each round, and transferring one unit of data spans the whole of one round. Therefore, demands processed in each round forms a bipartite matching, like this. An optimization problem is defined as follows. We are given a set of coflows, and we are also given release times and weights of all coflows. Here, Ri denotes the release time of the coflow Fi, and Wi is the weight of the coflow Fi. We have two types of constraints. The congestion constraints mean that the demands processed in each round form a matching. The release time constraint require that the demands in coflow Fi cannot be processed before release time Ri. The objective is to minimize the weighted completion time. Here, Ci is the completion time of the coflow Fi, which means that the time when the process of all demands in Fi is completed. Let's see an example. Here we have three coflows, F1, F2, F3. F1 is colored by red, F2 is colored by blue, and F3 is colored by green. The figure below gives an example schedule. In the first round, starting at time 0 and ending at time 1, we process these three edges. You can see that they form a matching. In the second round, these four edges are processed, and so on. The completion time is defined as the time when the last demand of the coflow is processed. In this example, the completion of coflow F1 is 5 because the last demands processed last processed demands are these red edges. Similarly, the completion time of F2 is 7 because these two edges are the last processed edges. The completion time of F3 is 6 because there are green edges here. Okay. So what is known about the coflow scheduling problem? The problem is NP hard, even if we seek better than 2 approximation algorithms. As for the positive side, 2 5 approximation algorithms are known. Both of them is based on LP relaxations, different from the time-indexed LP. These algorithms also show that the integrality gap of these LPs is at most 5. It's open whether these hardness and positive results can be improved. Also, many other variations are considered, and practical algorithms are also discussed. And here is our results. We show that the integrality gap of the time-indexed LP is at most 4. This is better than the non-integrated gap bounds of LP relaxations for the coflow scheduling. Our integrality gap result doesn't provide a polynomial time algorithm. In our paper, we also present another rounding algorithm for the time-indexed LP, which gives another polynomial time 5 approximation algorithms. Although I don't talk about it in this paper, in this talk. This result indicates that even if we care about the running time, the time index LP gives an algorithm as good as the other known algorithms. Now, let's give you the formulation of the time index LP relaxations. First, we let capital T be an upper bound of the time horizon, which is given by summing up all max degrees of all coflows. The LP has two types of variables. Variable x is defined for each edge and time t. It indicates whether E is processed at the tth round. T is defined for each index I of coflows. And this gives the lower bound of the completion time of coflow Fy. Then, the congestion and demand constraints can be represented by these inequality and equalities. We also have a constraint that bounds Ci from below by the average completion time of demands in Fi. The objective is the weighted average of Ci. We call feasible solutions for this LP fractional schedules. We prove that the integrity gap of this LP is at most 4 by giving a randomized rounding algorithm that produces an integer coflow schedules, such that the expected completion time of Fy is at most 4 times Ci. This rounding algorithm consists of 2 parts. In the first part, the fractional schedule given by the LP solution is modified into another fractional schedules of completion time of Fi at most 2 times Ci. This is achieved by random truncation and stretch. Then this fractional schedule is transformed into an integer schedule in the second part. This part uses the hypergraph perfect matching. Now let me explain the random truncate and stretch. We let alpha be a random variable sampled in the range from 0 to 1 with density function to alpha. Then for each edge E, let TE denote the time at which the alpha fraction of E is completed. We truncate the process of E at the time TE, and then stretch the time horizon by factor 1 over alpha. Here is an example regarding these red edges. The first round processed 3/4, and the second round processed the remaining quarter in the LP solutions. Then we sample alpha. So let's suppose that alpha be 1/4. Then TE for this red edge is 1/3, right? And thus its process is truncated at the time 1/3. Then the time horizon is stretched by factor 4 here. So this process goes from time 0 to time 4/3. After this operation, the expected completion time of each coflow is at most 2 times Ci minus 1. The truncation and stretch may make the process of demands change in the middle of a round. In other words, this gives a continuous time schedule. It can be transformed into a discrete time schedule by stretching the process of a demand more. So in this example, in the time from 1 to 2, this red edge is processed by so 3/4 fraction of this red edge is processed from time 1 to time 4/3 in the continuous time schedule. Then we stretch this process so that it goes from time 1 to time 2. So in this process, 1/4 of red edge is processed. So this modification may increase the completion time of each coflow, but it's by at most 1. So after this process, the expected completion time of Fi is at most 2 times Ci. So this is the first part of the rounding. Next, the rounding algorithm transferred this discrete time fractional schedule into a discrete time integer schedule. This is done by reducing to finding a perfect matching in a bipartite hypergraph. So let me explain what is a bipartite hypergraph perfect matching. A hypergraph is called bipartite if its node set is divided into two parts, S and T, and each hyperedge includes exactly one node from S. A perfect matching of a bipartite hypergraph is a set of edges such that it is pairwise disjoint, and also all nodes in S is included in some hyperedge of M. So now, from the discrete time fractional schedule, we construct a bipartite hypergraph as follows. For each demand, we add a new node, like this. In this example, this blue node corresponds to the blue demand. And this green node corresponds to the green demand. And this red node corresponds to the red demands. Then we define the hyperedge of size 3 that includes the new node and the corresponding edge in each round, like this. So, for example, this part represents one hyperedge that includes these three nodes. And there's another hyperedge that includes these three nodes, and so on. This gives a three uniform bipartite hypergraph, where the new nodes form the S part. Moreover, a perfect matching of this hypergraph corresponds to an integer schedule. In addition, the completion time of the obtained integer schedule is not increased compared with the original fractional schedule. Therefore, if we can find a perfect matching of this hypergraph, we have a solution whose objective value is twice the LP optimal value. Okay. Unfortunately, finding a perfect matching of hypergraph is NP hard in general. However, there are several sufficient conditions for the existence of a perfect matching, and one of them is given by Aharoni and Haxel. To describe their theorem, let me define the notations. For a subset X of S, EX is a set of hyperedges intersecting the set of E intersection T for each hyperedge E intersecting X. And HX is a hypergraph whose node set is T and the hyperedge set is EX. Then Aharoni and Haxel show that any R uniform bipartite hypergraph has a perfect matching if the matching number of HX is more than this value for each subset X of S. This is an extension of Hall's theorem that gives a condition for the existence of a bipartite graph matching. Perfect matching. On the other hand, Aharoni and Haxel's proof of this theorem does not give a polynomial time algorithm for finding a perfect matching. That is the reason why we have only the integrality gap analysis. Okay, so let's see the relationship of our hypergraph and the Aharoni-Huxell's conditions. The solution for the time index LP gives a fractional perfect matching for this hypergraph. This indicates that the matching number of hx is more than the size of x minus 1, or each x. Unfortunately, this is not sufficient for satisfying the Aharoni-Huxell's condition because in our hypergraph, R is 2, and so the condition of this theorem requires that the matching number is larger than 2 times this value. So this is not sufficient. But if we duplicate each round, and then we construct a hypergraph, as I did, then the matching number is double, and thus the condition is satisfied. This duplication also increases the completion time of each coflow, but it can be bounded by twice the original. So summing up, we have an integer schedule where the expected completion time of coflow Fi is at most 4 times Ci. Thus, the integrality gap analysis is completed. Let me conclude my talk. I show that the time index LP for the coflow scheduling has integrality gap at almost 4. We have a lot of interesting open problems. Obviously, one of them is whether we can find a polynomial time or approximation algorithm for the coflow scheduling. For this, one approach is to give a polynomial time algorithm for finding the hypergraph perfect matching under Aharoni-Huxell's conditions. I believe that this is not easy in general, but there may be a chance for the hypergraph constructed in my analysis, because my hypergraph has much more structure than the general hypergraphs. Another interesting question is whether the bipartiteness of coflow is essential or not. In my paper, as a minor result, I observed that all existing 5 approximation algorithms for the coflow scheduling can be applied even if coflows are not bipartite multigraphs. Thus, bipartiteness is not necessary for them. But my integrality gap proof uses the fact that the coflows are bipartite. Hence, my integrality gap result is the first result that separates the bipartite coflows and the general graph coflows. Finally, we also need some good hardness result. Currently, we have only 2 approximation hardness, which is for the concurrent open shop scheduling problem. That is a special case of the coflow scheduling. So we don't know whether the coflow scheduling is really harder than the concurrent open shop scheduling, which is another interesting problem. So this is the end of my talk. Thank you for your attention.